Welcome to this tutorial. I'm solving question number 10 of paper 2-1 October-November exam series of 2017. The question is mainly related to waves section of our physics syllabus. Question says figure 10.1 represents the electromagnetic spectrum. So we can see that the 7 components of the electromagnetic spectrum are given to us and they are aligned in the decreasing order of the frequency. So this end has the highest frequency and this end has the lowest frequency. While if we talk about the wavelength, then this portion has the least wavelength and this portion going towards the right gives us the component with the higher wavelength. So it says state the name of the components of the electromagnetic spectrum that is found in the region P. So in the region P before X-rays we have gamma rays, then after X-rays we have ultraviolet radiations, then we have the visible light, infrared, and after infrared before radio waves we have microwaves. The next part says on figure 10.1, mark a tick in all the boxes that represent the components with frequencies greater than the frequencies of visible light. So the frequency should be greater than the visible light, and we would be uh, placing a tick over here in the box Q. And lastly in the box P. Okay, the speed of electromagnetic radiation in a vacuum is 3.0 raised to 8 meters per second. A television remote controller uses infrared radiation of wavelength 9.4 into 10 raised to minus 7 meters. Calculate the frequency of this radiation. So the frequency would be calculated by using the relation V is equal to F lambda. So frequency would be equal to speed divided by the wavelength. The value of speed is given to us, which is 3.0 into 10 raised to 8, and the wavelength is given to us 9.4 into 10 raised to minus 7. So the answer we get over here is 3.2 into 10 raised to 14 hertz. So this is the required frequency, 3.2 10 raised to 14 hertz. Explain how infrared radiation is used in television remote controllers. So in these remote controls, we have infrared wave emitted by the control and it is received at the television set. This signal is encoded and whatever information was received by the television set that is being that is accordingly responded by the television set. Okay, the next part says figure 10.2 shows a ray of green light in striking the side of a glass prism. So we have green light which is striking the glass prism. This is the prism that we have, and we have a single color light over here. So the refractive index of the glass for green light is 1.5. On figure 10.2, draw the normal for this ray. Mark the angle of incidence with the letter I. Okay, so the normal would be made perpendicular to the surface of the prism, and it should be going through the point of incidence. So this could be the normal, and the normal is usually drawn in a dotted pattern, not a full line. So this is the normal, and we could label it over here. It is the imaginary line or the dotted line which is perpendicular to the striking surface of the medium, or the medium or the boundary of the two mediums. So the angle of incidence would be measured from the normal to the incident ray. So this is the labeling of the incident ray with the letter I. The angle of incidence is 57. Calculate the angle of refraction in the glass. So the formula to be used here is n is equal to sine of angle of incidence divided by the sine of angle of refraction. So the sine of angle of refraction would be sine I, which is 57, and the value of refractive index is 1.5. So when we take the sine inverse of the answer, we get the angle of refraction equal to 34. So this is the answer for this part. So the angle of refraction is 34 over here. The next part says, state what happens as the light enters the glass to the light's frequency. So it does not change, it remains the same. As far as speed is concerned, the speed decreases because the light is entering into a more dense medium, as does its wavelength. So the wavelength decreases. As a result, the speed of the light also decreases. On figure 10.2, draw the path taken by the light as it passes through the glass and into the air. So on the first refraction, this is the normal path of the light where it would have gone if the prism would not have been there. But since now the prism is there and it is entering a more dense medium, so it would bend towards the normal. So this could be the path followed by the ray of light when it enters the glass. Okay, now again there would be a refraction over here, and another uh, normal should be drawn over here. So this is a line which is perpendicular to the surface at the point of incidence, and again it has to be a dotted line. So now the ray of light would go in a way that it would bend away from the normal. So this is the normal path of the way, but when it bends away from the normal, it would go like this. So this should be the path followed by the wave or the light when it goes under refraction from the second surface. So this is the wave path which would be followed when it enters the glass prism, and then again it when it leaves the glass and enters into the air. So the question ends here with this part.
We try to explain complex concepts in simple language and with effective examples. If you like the video and the way we explain the subject, consider liking this tutorial, commenting on it and subscribing to our channel, and press the bell icon, so that you stay updated and get notified when we upload more videos. Thanks for watching.